Hello everyone, welcome to DFI India Groundwork Webinar 4. I welcome all the audience members for today's webinar and I'll give few of the instructions. Recording of this webinar is prohibited. Certificates will be prepared and emailed in approximately 2 weeks time. An online webinar recording will be emailed to you in approximately 2 weeks. Few of your attendee control panel details. If you want to hide your control panel to see clear screen, you can click on that red arrow button. If your GoToWebinar window is not in full screen mode, you can click on the third tab and it will make it in full screen. Anytime during the presentation, you can ask your questions to the presenter. Use the questions tab, put in your question and do not forget to put your name and your organization name. We have put few of the handouts for you to refer. You can always download those handouts anytime during the presentation. Now it is my pleasure to invite today's session moderator, Dr. Jaikumar Shukla. So he is Principal Engineer is Geodynamics Vadodara. Dr. Shukla is presently responsible for coordinating the technical development strategy, geotechnical consulting assignments for geodynamics since 2019. He is recipient of University Gold Medal for undergraduate studies and has obtained his PhD from IIT Bombay. Dr. Shukla is known for his technical proficiency in the field of geotechnical engineering and numerical modeling skills. He is actively involved in research and development activities and has more than 30 research publications written in national and international forums. He was executive committee member of IGS for the term 2019-20 and he has also guided many postgraduate students at MSU and DDIT. So I welcome you, Dr. Shukla, and I request you to take the session forward.
Thank you, Pranav. I welcome all the participants to this DFI's excellent initiative, and we need to, let's say, take away more on these things. I will go, not take much time and just move it further and introduce our session speaker, Mrs. Pranav. Can you just, let's say, yeah, okay. This is a sequence of groundwork webinar number 4. Let's say today's technical presentation is by Dr. William Cheang. He will be going to speak on underground infrastructure and metros, geotechnical modeling and analysis. We will further extend our sessions to some questions and answers at the end of the presentations, and we will also share some of the let's say upcoming DFI India's program details for another session of groundwork webinar number 5, and then we will end to this session. So I'll just introduce our technical speaker, today's technical speaker, Dr. William Cheang. This name do not require any introduction as such, because many of our Indian friends already know him, because he is one of the best let's say PLAXIS trainer which I came across, and everybody, or say most of you are agree with me. But on a, let's say, good note, and let's say DFI's platform, I just would like to introduce Dr. William Cheang. Dr. William Cheang obtained his let's say bachelor's and MSc from University of East London. He holds a PhD from National University of Singapore, specializing in the field of geotechnical engineering and computational geotechnics. He is currently a principal consultant geotechnics field at the Bentley Systems and member of Geotechnical Research Editorial Board, Institute of Civil Engineers, United Kingdom. He is attached to geotechnical industry for past 20 years as both as an engineer and consultant, and believe me, he is the one-point contact for all geotechnical finite element applications and questions and answers. So I welcome Dr. William Cheang for this excellent session, and all the DFI India participants will eagerly waiting for your session. Now I'll just hand over the session to William.
Hi, I hope everybody can hear me. So Pranav and Dr. Shukla, can you hear me loud and clear before I switch off my video because to save the bandwidth? Can you give me
Yes.
information that you can hear? All right, so good. First and foremost, I would like to, on behalf of the team, the work that I'm going to present is not entirely of my own. It's out of collaboration amongst the members of the Bentley Geotechnics. Many of you probably know by now that PLAXIS was acquired 2 years back, and now we are part of the Bentley Systems, and we have a special group in Bentley Systems known as the Geotechnical group. I hope, first and foremost, good evening from Singapore, and thank you very much for giving us this opportunity to share with you our work, our vision, and perhaps some of the solutions that we are going to show tonight or this evening can help you or give you some ideas of what you can adopt in the coming years. Now, for the past year, I think with the pandemic, this is a very challenging time for all of us. And just before I switch on to this webinar, I was heard from the news that you have a new lockdown in India. So I hope, especially in Delhi, Mumbai, and hope that everybody is fine here. So I'll begin the webinar by showcasing, first of all, giving you the introduction first. And this webinar is on the underground infrastructures and metros, part of these geotechnical modeling analysis webinar series that I've been doing for the past year with my colleagues. And before I move forward, I'd like to thank my co-workers, my two main co-workers, Rajendra Bish and Sapar Rajabandri. Rajendra is based at our Mumbai office in India, and Sapar, he's based at our Sydney office. And some of this work and some of the work you see later is out of this collaboration. And this webinar is on the technical analysis of underground metro infrastructures. We are looking to look at linear and also sort of a local type of construction. We will also look at some of the issues that we should look at some of the issues. I'm trying to get my pointer out here. It's just that with the pointer out, I can't scroll my mouse. So let me move back one slide so that I can actually get the key points from my script. So we'll focus squarely on our geotechnical solutions. Please bear in mind, this is not a sales and marketing pitch. It is entirely out from our work supporting our clients and our key workers in this region, that how some of these methods came about. Yeah. And the challenges in any of these metro works is that excavations for construction of station boxes and underground metros are getting a bit more complex nowadays, especially more so when we're looking at interoperability. We're going to look at some of these things. I'll show you some examples on excavation, tunnels, and data modeling. And most important of all is to show you some innovations that we have built. I didn't build it, it's the team that has built it. My part of the work is to show how these sort of innovations can work here. So next slide is, I want to put a statement here from ground to cloud, connecting with the future to geotechnical solutions. The reason being is that all the nations in this Asia region and also in India is that we are more connected than we think. How we share information, how the data is being uploaded and shared across different disciplines. And I would like to coin or put in a statement here that from ground to cloud. So basically, it's how we are digitizing our solution and how we are interoperating with the future solutions. You'll see some of this in the coming slides here. Apologies to save bandwidth, I will momentarily turn off my webcam so that you can concentrate on the slides and you hear my voice here. So I'm going to turn off my webcam here. All right. Okay, can you see my screen, right? But I'm going to switch off my camera. Pranav, can you switch off my camera, please? All right, thank you. All right, can you see the screen right now? Can you see my slide from ground to cloud, connecting with the future? Yes?
Yes, we can.
All right, let's proceed. Thank you so much. Now, this presentation, I will break it up into 4 parts. First of all is the introduction, that's part A, and part B is to technical analysis and interoperability. And in C, I will show you some examples of analysis, nothing very deep yet, because I was reminded that those are sitting in the audience, some of us may not be involved directly with your technical engineering. So I want to keep this slide as easy as possible. So for the pleasure and those sitting in, so that you can actually pick up some of the points that we have that I'm going to share. And the part D is I will talk about showcase some of the case examples. These are all some of the winning entries of the year, the infrastructure here. So first and foremost, what is it that we call the cloud-based type of solution? Basically, it is the ability to share information. Now, to allow this information to be shared across various disciplines, various softwares, and forming a solution. We have this thing called a connected data environment. This is the what we call the CDE. The CDE serves as a hub where informations are shared. Now, on the screen here, you'll see that there are various types of constructions, or various types of, if you look at in design and modeling, various types of applications, right? If you look at in terms of rail and transit here, you have look at subsurface utilities, wind farms, offshore, power plants, building cities, constructing water and wastewater, nuclear power plant. Now, all these, if you look at it, right, when would you not need geotechnical engineering for any of these developments and infrastructure project? If you look at it, everything that you build is either beneath or on top of the ground surface. So this makes our work as geotechnical engineers very interesting, because you may build the most beautiful structure, right? You may build the most wonderful thing, the most expensive thing, but if the foundations are not strong, if the ground itself is not able to support this sort of structure in its sort of working life, then that is a bit sort of concerning, isn't it? So what is also more important is the interaction of the structure with the ground and its response to the loadings from short-term, transient, and long-term conditions. So for those sitting in, many of you know that I've been with PLAXIS for many years. I'm still with PLAXIS looking at computational geotechnics. So computational geotechnics allow us to assess these type of superstructure, substructure, and time interactions. And to do so, and to do these things in the future, there's actually a reason for us to move into this connected data environment because of interoperability, right? The design analysis of tunnels and excavations demands careful coordination across many disciplines, including civil, geotechnical, structural, and hydraulics or hydrology, even environmental, if you look at it. A common modeling and data environment enables us to use digital information to design and analyze. So perhaps let me show you next slide, see what I mean. Now, if you look at this animation here, 30 years ago, our industry was living through the digital transformation of CAD, right? CAD, computer-aided design, which was taking what we were doing on paper and moving that into computer. Right, this we recognize, because you go back even 20 years, this is how it was. Now, the next disruption was when we moved from CAD to BIM. BIM is building information models in 3D. Now, our industry is advancing beyond BIM. And for the last couple of years, we have been working hard at adding the missing dimensions to digital twins. So this whole interoperability that I'm going to show in conjunction with the modeling of excavation tunnels fall into this realm here. This dimension of context, dimension of time now is, in terms of modeling, is part of this so-called digital twinning here. So what is digital twin? If you look at the digital twin workflow, it's a cycle, it's an iterative process. It's going to loop and loop. Now, if any projects, you're going to start off with planning, site survey, reality modeling. You're going to look at macro level type of modeling, perhaps even as far as the citizens engagement as well, right? Now, once after you have these completed, you move on to design. You engage your stakeholders, you plan, you visualize, you do your design review in collaboration. Now, then you move on to analysis. For example, structural analysis, geotech analysis, flood analysis, and what else? Even traffic analysis, right? And you construct. Now, once you construct, you're going to move into the operation mode, maintenance of the infrastructure or the facility you have built. And still, you need to continue to manage and maintain this facility that we built. Now, having this digital twin is that the digital lives across the whole life cycle from the concept to the operation and maintenance, and enables a digital workflow as collaboration, review, and simulation and monitoring. So this is what I'm sharing here. It's a very mild concept of a digital twin. So geotechnical analysis will definitely be connected in this whole loop here. Basically, is you have a physical infrastructure that you're going to build, but your digital twin, which is exactly as representing that physical infrastructure, but in kind of a virtual sense. But that virtual sense is just not a model. It has ability to react based on the data that we fit in, and also the monitoring that we fit in, right? So for example, if you look at first and foremost, I want to explain about what we call the in terms of the digital twinning. You have things like constructing a building, or you constructing excavation. Constructing excavation is going downwards, right? Going downwards. Now, if you construct an embankment or you construct a road, this is what we call linear type of modeling and analysis. And this is important because with reference to the solutions that we have in the system, is that this will require a different set of solution. This will require different sets of solution because it's linear, especially more so when we're doing geotech. We have a piece of infrastructure that transect maybe 100 kilometers of changing ground. Whereas for a building here, you just need to go downwards and pretty localized when compared to the linear type of infrastructure. So let me show you one case of a digital twinning. And in the digital twinning, this model on the right-hand side will be constructed first for planning and for visualization, for engagement with the client stakeholders. And once you progress in terms of analysis and design, the level of detail here will be improved and increased. And to the point that when this is all built, right, you even have the information to sort of coming from the monitored system. So this was based on one of the very successful digital twin project. Many of you sitting in this room probably you have seen and heard it before somewhere. This is from the Crossrail in London here. So on the left is the physical railway, and on the right is the digital railway. The same concept can be applied to many type of infrastructure. But what I want to do is to show you left and right. The right-hand side is a twin, and the left-hand side is that physical infrastructure. Yeah. So how do we do this? We are not in my current presentation itself, because Geotechnics is still very new. That means the incorporation of Geotechnics is still at the very start. Yes, you do have projects whereby the whole digital twin is being implemented, but a lot of infrastructure work right now, as far as I know, in my opinion, is that it's not many projects that they have fully come into developing this type of digital twinning. But we are on the way. We are on the way to do so, because for us in the Bentley system in Geotech, it's just 2 years once you join the company. Now, this is going to be part two. Part two is that I'm going to begin by looking at interoperability and geotechnical analysis. And what is interoperability? The key thing is that a good interoperability, a good interoperable solution expands our capabilities, but not timelines. Yeah, that is supposed to enhance our work, reduce the errors, and then expedite the design and modeling analysis here. So, what's the value interoperability? In the presentation, we are discussing the value and interoperability. So it saves time by increasing efficiency with advanced digital workflows, improve reliability through reducing risks and errors with trusted information and sound computation, and advance our expertise as geotechnical engineers and collaboration to ensure you can make responsible data-driven decisions here. So currently, there's no comprehensive solution for excavations and tunnel planning or any infrastructure planning and design, and that can bring different disciplines together under one single interoperable workflow. As a result, massive data management between disciplines is required. It typically leads to errors and coordination problems. These massive data needs to be reproduced for various disciplines, which means that for structural engineers, although we're working on the same design, they will have their own sets of drawing. Geotech probably will have a set of drawing, but then it doesn't get updated quickly or reflected quickly, then hence you get all these hiccups. The industry relies on a multitude of non-tunnel specific authoring tools. Probably you have heard of other different types of solutions, and which makes it also very challenging because which is the type of file format can you cross as change? So for us, it also means that when we're doing geotech, we will need different software for each of the discipline, causing both technical and operational problems. So imagine if these challenges, these sort of issues can be solved by linking these sort of data, and to ensure that the flow of data from one discipline to the next are properly shared, effectively shared, and hence also properly updated in time to speed up the modeling analysis here. Okay, now this is what I mean. Typically, if you look at some of the solutions that we have been promoting, is that a lot of work begins from the site condition. You need to assess the site condition. Then you have some sort of concept, putting on alignment. Then roughly you get the size of, let's say, the tunnel alignment, the diameter, and the highway height design. And perhaps right after you have the alignment, the structure that is needed to support it is there. So once this is set, then perhaps we move into a more in-depth site investigation to characterize the ground, to get the soil parameters, and also to derive the model parameters. Then you do the analysis and you have the review. So roughly, this is what we think will be good for the industry. I mean, having these flow whereby the connection of all the disciplines are linked up in a bit by bit sort of concept. Yeah. So this whole thing will need something that we call a common data environment, as I've shown you much earlier. So I've shown you that big picture in the earlier part of the introduction, and to the points that I've raised, the issues and the challenges, and how we should do it. Now, this is that typically the environment. So the take-home message, if you can leave this section today, is that we need this common data environment to allow all these four major disciplines to cross-exchange information, and this will allow us to perform better modeling analysis and design here. Which brings me to the next one, which is in part is what I've been asked to do, is that because many of you sitting in this webinar today definitely have heard our work with PLAXIS, PLAXIS 2D and 3D. PLAXIS is a finite element type of numerical approach, and since year 2020, we have the change of the logo, and we have a change of the version, and we have also changed in terms of how we are connected to the system. If you see the Connect edition here, it means that right now PLAXIS is part of this whole ecosystem. right? This whole ecosystem. So it's important to have this Connect edition because it allows us to grow from ground to cloud. Now, for those of you sitting in today, you are probably very familiar with PLAXIS 2D and 3D. Apologies on the screen here if I still use this PLAXIS Modato. This is no longer called Modato. It's called the PLAXIS Monopile Designer. And well, so this is PLAXIS. So PLAXIS is part of this whole Connect edition. So right now we are at version 21. Version 21, I think you can probably have guessed that represents the year of the edition here. So PLAXIS Connect edition version 21 is the latest release of the software. Now, just to remind yourself, also for those sitting in, perhaps you are not very familiar with PLAXIS. I won't be showing you how you work with PLAXIS. This is not the order today, but I would like to take this opportunity to also demonstrate or to show the versatility of the interface. The interface looks very simple, and the simplicity of the interface that what makes a lot of clients happy. Because when you look at the 2D version and the 3D version, they are almost exactly the same in terms of the features, or in terms of the options in the graphical user interface. More or less, yeah, the same. Now, on the right-hand side is the 3D program, and on the left-hand side is the 2D program. And this is the working area for both. This is called a drawing area. Then you have a command line, command area. And on both sides of the screen here, you can see the Explorer boxes, which we use to manage the modeling and analysis. And what is important is that some of the audience sitting in today are very new to this. And what is important is that the ability to recognize that there are always 5 modes in PLAXIS. And these are the 5 modes. These 5 modes are very important. I've been teaching PLAXIS for the last 10, 12 years. And although the modes you're looking at is, okay, what is he or what is William trying to teach us? Well, a lot of times when we troubleshoot the problem, or we try to explain to the users some of the new tool sets, the Geotechnical stuff that we have developed, it's very important for me to tell you where is it located, because if I don't tell you where is it located, it's going to be a bit difficult to locate these features. If you're modeling tunnels and excavations, well, these 2 parts, it's going to be very important, because these 2 blue modes, it is the one that where you construct the geotechnical model. When we talk about construction geotechnical model, it's just not about the geometry, whether it's in 2D, 3D, or it's also concerning the material representation. Before you can even prescribe the material representation, you need to characterize this kind of soil. So this is the part that you need to be very careful, because this is what we call the idealization part. So those students seeking in is that the world is always 3D or even 4D with time, even more, right? And if you attach money to it, it's 5D. Now, if you look at modeling, the problem is essentially a 3D problem. So with time, perhaps you put another dimension to it. How do we bring the model into PLAXIS 2D and 3D? It is something that a skill set that you will need to build. Although there are rules, although there are people there to help you, to guide you, although the experience to guide you, but a lot of times we need to sit down and think about this problem that I'm looking at the site. Should it be modeled as a 2D or the 3D, right? So these 2 modes, very important. And finally, meshing is to build up that mesh so that you can compute. And the last 2 part is also very important, because you can build the model in 2D, 3D, but at the end of it, if you're not simulating the correct sequence, you're not simulating the correct thing, it's going to be incorrect. So knowing what's happening in situ, right, and knowing what you want to capture, right, you need to build up those sequence of the faces in these 2 modes here in PLAXIS 2D and 3D. So here in PLAXIS, we have this intuitive modeling workflow, the 5 modes. PLAXIS 2D and 3D in conjunction with some of the options. If you're talking about modeling of tunnels, you have the tunnel designer module for that you can use. Sometimes, though you're looking at an excavation problem, now the problems you're looking at right now, yes, first and foremost, you've got to ensure the excavation is stable and the deformations are well contained. But then your excavations, you might have a tunnel coming in later, or you may have even an existing tunnel right there, and then you build a station box next to it. And this later part is what we call the building or construction damage assessment that we need to check. Now, to do so, I will have to rely on some of the new things that they've built called the interop stuff with the structural analysis tool sets to build a structure next to it, right? So how do we do that? In our system, the PLAXIS is now, especially the PLAXIS 3D, is now integrated with STAADPro and another structural program to the ISM. ISM is called the Integrated Structural Modeling. This workflow allows us to consider the influence of buildings during the tunnel substructure, superstructure interaction. And ISM is a workflow process. It's a user-friendly platform, and the solution or the software is equipped with advanced features to tackle modeling challenges in the most complex geotechnical execution tunneling projects. Okay, now I'm going to move on to the next slide. So just to give you an idea of a big picture, what I'm trying to achieve is that, well, you have perhaps a tunnel going beneath an existing building. Now, this building itself, if you look back many years ago, to incorporate this building into a PLAXIS analysis or in any geotechnical finite analysis, roughly we could do a first approach whereby you have the footprint and perhaps you apply the load to sort of simulate the influence of the building loads. But in this day and age, this is not going to be enough, because to look at the impact, the geotechnical impact and the structural impact and the hydraulics impact, a proper representation in the building is important, because the weight, the stiffness, and how the weight and the stiffness changes the effective stresses and the pore pressures here. It's going to be a very important detail to pick up. Now, the tunnel will drive too. Of course, you can figure out I can do any fancy tunnel, sweeping around, cross, not entirely going through it in the center line. But for the purpose of demonstration in the coming slides, I just want to show you that how this model now can be built in this whole interoperability work process here. This work process uses the integrated structure model, and the structural synchronizer is the core component of this whole ISM workflow. And this process involves creating a repository of common data environment, which is known as the ISM repository, from any ISM-enabled solutions in Bentley. While you're creating the repository, the structural synchronizer allows you to selectively save the desired objects and properties into the ISM repository. Other ISM-enabled products can then import and make use of this information that's being stored, whether it is going to the geotech analysis and modeling, whether it's going to the civil side, or whether it's going to the building side, whether it's going to the structural side. Right now, in some ways, we can solve it. So the interoperability is two-way, and anytime you can update the program with a new data. So what am I saying here? So you have the structural synchronizer in the middle, and how it cross-exchange information from that central hub here is to pushing and updating that repository from the various solutions and Bentley systems, geotech, structural, and the civil side here. ISM is free to users of any structural product from Bentley. And just to give you a big picture of what I mean by having the ISM standard is that right here is supposed to be, apologies for you sitting in, if you find there's the logo is missing, It's just that I've accidentally deleted. Here is where the PLAXIS Geotechnical a solution sits. And basically, if you look at this, it serves as a hub, and then it can be actually transferred to all other solutions in the Bentley system. So this is the big picture that I wanted to highlight. Of course, many of you sitting in today may not know all the details of all these. I don't even know, because this belongs to the other groups in the Bentley system, the structural side. You have the building side, then you have some other part of the beam side. So the geotech one is supposed to be here, and it's supposed to be linked up with just a line. Now, this is a short video which I would like to demonstrate how I can bring a structure into geotechnical analysis, and from there onward, perhaps I built a model whereby I put an excavation pit or put a tunnel next to it. All right, so I would like to demonstrate how I can bring in this information. So this video, I'm going to sort of narrate it a bit, put a voiceover. So you're looking exactly a model of a 10-story building in a STAADPro program. So 2 lift course in the middle, just to show you some of the details of this building. And right now what we do is that we're going to create a repository and upload it into ISM hub here. And this is the model that we're going to upload it to the ISM repository. And you select the objects that you wish to upload. So I selected all, and it's uploading. I've shortened the upload time because you see it's already 100%. This took me about 20 minutes because it's a huge chunk of information. And right now, I'm back at the PLAXIS 3D model, a PLAXIS 3D program. And I will begin by configuring the my remote scripting server so I can log into the hub. And from there, once I log in, I will call upon these model that I have initially created in STAADPro. So loading, again, communicating with the ISM structure synchronizer and update. And right now, PLAXIS is reading the file, synchronizing the information. And if you look at the structure that is going to be formed at the back, is that the structure itself, it is represented with the beams and plates in the PLAXIS 3D. Now, once that structure is being built on top or in any of the positions, then I can continue from within PLAXIS 3D to construct an excavation next to it, or perhaps what you saw earlier in the presentation, a tunnel that actually goes beneath the building, about 2-3 diameters below the rail foundation here. Okay, now that was on the structural side, but let's talk about the civil side, because the structural side is concerning with problems that is localized around a region. That means you're either going up and going down, right? Now let's look at some of the civil solutions that now from a geotech that we can interoperate. A bit of a selling here, I mean, not too much, just to give you an idea that what is a civil designer in the Bentley systems is open rails, is concerned with the construction of linear infrastructure, sorry, and this is that interoperability, that integrated workflow. On the top part is where my civil colleagues will be doing the whole conceptual modeling, so by capturing the terrain, then moving that terrain into a concept station of the program whereby the alignment is placed. Once alignment is placed, for example, for tunnel or even embankment, and then we move on to the detailing. Detailing means that the design of the size of the tunnel or the height of the embankment, and thereon perhaps there'll be other structural items that need to be included. For example, if you have a tunnel alignment, you have say 20 kilometers of tunnel boring, and then followed by a box station, For road embankment, perhaps you will have that approach embankment coming in to connect it to the bridge. So this is all part of this what we call the civil solution. And you can see that right now, this is where I'm going to be able to link up with this sort of system, because all this part here, for example, once they design the cross section is then sent, or perhaps you're looking at a particular segment of a 2D, a 3D analysis of a tunnel. That block is then passed on to the geotechnical analysis, right? Whether it is for a stability deformation, excuse me, or entirely of a limit equilibrium analysis using the SV slope, or what we call right now the PLAXIS limit equilibrium analysis. With this box here, this ecosystem here, we can still pick in information from, let's say, from GINT, bringing in additional soil information to update the model. So this is the so-called vision of this whole interoperability and in the integrated design workflow. And the next slide, I want to show you this very interesting from concept to the design. Now, this is not PLAXIS, yeah. This is not geotech analysis, yeah. This is where we work with infrastructure team, and they are the ones who are given alignment, and they start to build things around the alignment. For example, a tunnel, and even a station box later, which I'll show. And what is interesting right now is that the technology is such that the building of this model, it's more or less programmed in a way by what we call node and interlink. You can see here, this is a programming, but the programming is tied in terms of how you link one of the boxes of information and how it controls the subsequent detail of the beam model. For example, you may have alignment of different radius. If you shift it, you don't have to demolish the beam model. The whole thing will be updated automatically. Or perhaps you want to change the thickness or the tunnel segments. These are all updated. Now, this is a very smart tool. This is called the open roads, open civils, plus the what we call the generative components, the GC components. This is the GC components. So what can we do? Well, in future, you're going to see more of these things are being seamlessly connected to geotechnical analysis. But right now, in my analysis here, for example, I will need the alignment and the diameter. And perhaps when we move into a part whereby the station boxes, we need to do the analysis. Again, this is coming from the infrastructure civil team. You can see that this is all visually well represented, and the level of detail is pretty good. But for geotechnical analysis, I mainly need the bigger envelope. I need the envelope of this box. I need the position of the basements, the center line of the basements, and this is something that you can build right now. Not say automatically, but at least you can see the direction of advanced technical modeling is that now we are much more able to connect with the digital twin or the BIM model. So this is the model that was an outcome of collaborating with the infrastructure team. Is all we ask for is that a level detail of 100, give me the envelope, give me the position of the basement, give me the time sequencing, and with the boreholes around it, I can just build this model. And each of you, those who are sitting in here, are very familiar with PLAXIS, you know that this model is not a very hard model to construct because it's rectangular, and this can be done in just less than, if you're fast enough, it's just less than an hour. But you can see right now the connection, that how we are linking up with the rest of the solutions here. Now this one, it's an example. I'm showing an example of how these things finally linked up in this tunnel and excavation box in terms of interoperability. Here is an example from Gothenburg in Sweden, and Gothenburg is the second largest city in Sweden with nearly 600,000 inhabitants. It is expecting to grow significantly in the next 15 years, adding 15,000 new residents. What you're seeing now is that how we can use a digital context interoperability of a city to visualize planned and designed a new 8-kilometer tunnel under the central district. They linked in data about the 3 new stations. If you look at this whole simulation again, right? This whole information, they linked in the data about the 3 new stations, which includes a rendering, what the stations would look like. And since this is a buried infrastructure, there are sliders to control the transparency of the surface layers to easily see the tunnel. This rail line or this tunnel and the station boxes is seen as a critical piece of infrastructure to enable the sustainable growth and making commuting within the city more efficient. And also for the stakeholders and things like this right now, like this is all web-based, and it is part of this whole the planning, design, and management sort of like a discussion presentations here. So this is a very nice solution. And of course, the next vision is that many of you probably have heard that probably be using this before, is the use of INSAR in conjunction with conventional monitoring. INSAR itself allows us to look at ground settlements, and you look at this as an example from the this is part of London, and then you can see these red lines here. This is all being inferred from the INSAR, or what we call the interferometric synthetic aperture radar. Is part of a deformational study, something that in the future this can be used in conjunction with the analysis and how we present the infrastructure with the monitoring data. This is advanced technique of monitoring, and this in conjunction with conventional methods can be used to enhance our ability to make predictions in our analysis here. Okay, that was part A and part B, and part C right now is that I want to bring the audience into a deep dive a little bit into the modeling of excavations and tunnels and tunneling. Previously, the part A and B is about giving you that vision for the future, how the future might look like in terms of the geotechnical analysis and interoperability with the rest of the modeling groups here. So modeling of deep excavations, I've been asked to provide a short explanation for the benefit of students and people who want to embark on geotechnical analysis. Numerical analysis of deep excavation involves modeling of multiple excavation stages. It involves the soil structure interaction. It involves changes of groundwater level. Well, it involves a very complex retaining system where the soil transfer the load to the system, and the retaining system sort of reacts back to the soil, and hence the ability to model the structural system is also very important. This is so connected to an earlier part of my presentation, where we have the interoperability with the structural analysis solutions. And even more so right now, we can build a safe structure in terms of the limit states, ultimate limit states, but we must also ensure that the construction and the structure that we build on top or within the ground, it does not impose too much of disturbance on the surrounding structure. So this is part of the whole construction or building impact assessment, and which needs to be assessed. You shall see in one of the case history later. So these are the type of the generic issues that we need to take care when we construct any excavations in urban areas here. And to do so, we need to have the ability to capture the complex response of the soil. You can look at the stress path, stiffness level dependency, strain level dependency, isotropy, and this sort of things. But one of the most important one is actually stress paths as well, because if you can't properly capture the response of the ground in situ, you're going to end up with the wrong prediction, right? And to add on further, excavation normally involves this sort of primary loading and mainly unloading, reloading. It occurs in different zones of the domain of the excavation problem. In some areas, you can be dealing with very small strain range, especially in a very far field area. And closer to the excavation box, it gives you a you normally go to a very large strain problem, and the change between these two ranges will sort of give you the sort of deformation prediction that is very important to capture. And hence, using simplistic linear elastic perfect plastic model, especially more so in normally consolidated kind of soils, is going to be not the correct thing to do. So simple elastic perfect plastic models is just not sufficient to look at the pre-failure deformations, because of all these things here that you need to account for in your modeling. And just a rough, just a quick indication of the type of soil models that we have before I jump into the geometries, is that it's just not sufficient just to look at the molecular model, to use the molecular model in modeling, because the hardening soil model is not a very difficult model to appreciate and understand. In fact, this model itself is no very difficult in terms of parameters, and by and large, in many of the regions here in Southeast Asia, especially in Hong Kong, Singapore, and in Bangkok, these models is almost a default right now, these two models. In some companies and some of these practices, even a lot of clients begin with the HS-MOR model without any big issues here. So this is a standard library model, and this is the user-defined soil model. If some of you wish to do this advanced work, you have these models that can help you to sort of capture almost most of all the soil responses. Of course, I've mentioned earlier the structural elements. You have the plates, the beams, you have the embedded beams. If you're talking about 2D kind of modeling environment, because it's plane strain, then you're talking about this embedded beam row. And in 3D itself, it's no longer a row because the spacing is explicitly captured here. And in terms of soil structure interaction, of course, you need the interfaces, and then some other type of modeling, you will probably need these sort of things as well. Yeah. So just to give those who are sitting in who are new to PLAXIS, these are the type of models that we have incorporated into the analysis, or in the options here. Again, the workflow, just to go through, you have the soil structures, mesh, flow conditions, and stage construction. And moving further ahead, as I said earlier in the beginning of these presentations, you can either model the problem in 2D and 3D. There's no a guidebook that says that, well, all these problems are located in this site has to be 2D or 3D. You need to make that judgment call, educated judgment call, to say, okay, at this point in time, I will do 2D for certain reasons, or perhaps this model should be done in 3D. So one of the best sources that I've managed to sort of put out is by Professor Matos Fernandez. It's from one of his book, and I have incorporated in this presentation here, credit to Professor Matos Fernandez, is that these are the things that we need to consider when we are looking at 2D, and this is the sort of things that we need to incorporate when we look in 3D. And of course, most of you sitting in today is that, well, if I have 3D, why do I need to be bothered with 2D? The reason is this: there'll be times whereby, for example, let me give an example, is that at the very initial stage of project, the client may not have the kind of finances to sort of support a full-fledged analysis. Perhaps a 2D analysis is something you should do quickly, just to make a set of check, and followed by whether it is necessary to do a 3D. Well, and sometimes bigger companies say, well, let's not bother with 2D. I think we have the resources, let's deep dive into 3D. And the reason is because, like, for example, you're dealing with excavation, is dealing with multiple cells. There are 2 cells here, right? You can even have 3 cells, for example. And for those of you who have been to Singapore, you look at the Marina Bay area, the 3 towers there. The foundation itself, the pit, was actually begin with these sort of multiple cell excavation going down to build up the basement and the foundation system, and then the towers built on top. So these are the sort of things that will require a proper 3D analysis. Added some slides here just to comment on the idealization. On this slide here on the left-hand side, demonstrate the ideas of a 2D analysis. You have a problem like this in terms of geometry and the loading pattern, which is of constant from one end to the next end, then the 2D analysis is a very relevant analysis. There's no point for you to go 3D because you're just going to bump out your time and even increase the cost, right? But of course, on the right-hand side, you have problems whereby it is essentially a 3D and it's no plane strain conditions have been met, then you need to perform a 3D. So the key thing is having the ability to identify the problem on hand and how you translate that model into an analysis, an amount of level detail that you wish to incorporate into the analysis, right? So here marked by the level detail. So for example, you're looking at just a very simple a water inflow of the tunnel, perhaps is a first level analysis, perhaps a plane strain model is sufficient. And perhaps that based on your experience using the PETA method, those who are sitting here been to our advanced courses who know what the PETA method is. And with the PETA method, you already know what sort of stress relaxation that you need to incur, like sort of a volume loss, and you want to look at the impact. And because this model having two layers, right, is better than your elastic solution because this is modeled by the HS Moore, and this is also HS Moore. And then this is a much better sort of settlement trough prediction than of Henckels, for example. So then your 2D analysis here, it's still very relevant. Now, moving forward, there will be in many situations in tunneling that you will really need to do a 3D. For example, the impact analysis that I've mentioned earlier. You probably have these tunnel moving in, and to some point you hit a problem whereby you need to do some sort of intervention, right? So whereby the tunnel cutter sort of stop for a period of time, and what sort of pressures that you're incurring in the front. And of course, the biggest worry is that what sort of movements are you incurring? So these are the sort of things that you need a 3D analysis. Now 2D on the left hand side is still possible, although you look at the pit like this, it's still possible. And on the right hand side is to give you an idea of what could be a 2D analysis, or how a 2D analysis would look like for a basement analysis. This I pulled off from one of my colleagues, and it's actually a shaft, a square shaft, and a basement that a client needed to construct here. So I'm just showing you in terms of how the model looks like, how it's being set up in terms of plane strain. Now, of course, moving a little bit more forward, you have the plane strain model on the left hand side, and on the right here is in the middle here, it is a 3D analysis, but in fact it is actually known as a 3D unit slice or 2D 2.5D model. It's not a full 3D model, it's a 2.5D or what we call unit slice. I wanted to mention this is because that I wanted to add some value in for those who are learning geotechnical finance and element analysis, knowing what sort of models that we call help us to envision our work and help us to even communicate properly and technically with our co-workers. Now, you have the 2D plane strain. If you look at this problem, because the layers are all horizontal, it's consistent from the front to the back, and the struts are all consistent from front to back and going down, and hence this actually is a plane strain issue, is a plane strain solution. Now, if you try to model in a 3D unit slice, you can, no issues. Just that what I'm trying to demonstrate here is that there's no need to do so, because you see the 2D model gives almost the same result as almost a 3D analysis in terms of a 3D slice. So what am I saying is that let's be very smart with our work. There's no point bombing out analysis whereby you build this model, but this in fact could have solved it, because this is actually at least half the effort needed to do this. And in terms of interpretation of the results, it's half of this at least, right? Now, this model will not work if I go forward later, is that one of the struts here where you need to access a pull out, that means that it stops, right? So I mean, you need to model a one strut failure. Apologies. You cannot use a 2D then, because by pulling the one strut, you are then pulling the whole row. So in that sense, a 3D model would be the way to go. So you need to really ask yourself what you're trying to capture. Then you can actually identify which modeling space to do, and that is very important. I mean, I don't need any fancy 3D graphics. It's like getting the correct response, right? So this is another one. Instead of say using a half 3D, it's a shaft problem. I modeled as a plane strain. No, sorry, I modeled as asymmetry, because this cross section here under the asymmetric space gives us the same response as a full 3D. And this is what you're looking at, is a half model of a shaft. In fact, if you're a bit more sort of you want to save in terms of computational time, you can model as a quadrant, because the quadrant also represents the whole 360 sort of condition around the shaft. Because you look at the layers, you look at the loading pattern, they are all constant. There are no significant changes in terms of the profile and the loading conditions. And if you look at even for some, you can see in some literature that not even a quadrant, even maybe a radian sort of like a slice of it, I mean, index of radian sort of rotation will also give you the same thing. It isn't properly set up. So again, it's to demonstrate that you need to really understand the conditions of your problem to be able to build up the model. And coming forward, looking at excavations in terms of a modeling space, on the left-hand side is the quarter model. So when you look at the quarter model in this sense, if this is 10 meters, you're basically modeling a 20 by 20 meter excavation box going downwards, right? Of course, if the width itself is 20 meters, is the length itself is 30 meters, you can still build in certain respect the quarter model. But this quarter model will not work if the loading pattern around it or the ground layers, they are no longer sort of a uniform or consistent in the three axes, right? So this is what we know as the quarter model. So for those who are sitting in, you can have a full model, you can have a half model, you have a quarter model. Now this is the half model. This half model was essentially made and not entirely of a unit slice. The reason being is that we wanted to study the effects, the influence of, if I were to experience a one strut failure at the most bottom strut here, I mean, what would be the redistributions of the forces around these zones? I mean, you can of course, the deeper strut will carry quite a lot of heavy load, and normally this is the one we pull to see, because this is when the excavation height is at its most extreme, and we will see the redistribution. Some even pull one, some even pull two, and you can't do this modeling with in 2D plane strain, because if you pull one strut at the bottom level, you're pulling away the or you're removing entirely the whole strut and that level is a. So that is why, although you can see that the model here, the ground layers may be consistent, uniform, but because we needed to capture that very localized effect, this is the 3D model that we have built here. So this is after Dr. Kamchai and Dr. Kamchai Tongs, a student of Professor Matschweiger from Graz, and I've put in this title. The paper here is published in the ASC, a very wonderful paper to read, and I would like to encourage you to take it up to have a look here. Some other 3D models. You can see if you look at in terms of building impact, this was for a case in Singapore. I've removed some of the details just to give you the shape of the excavation, the multiple cells with the a few of these super beams across. This is very something a lot of the contractors would like, because it opens up this area. There's no congestion, and then it starts sort of building up things, and then and it can be easily removed once this are incorporated into the substructure system. And one of the reasons and aims of this analysis was to look at the impact of the constructions on the existing tunnels. And before we started this work, we needed to capture the history of the soil stresses around these two tunnels, because the tunnel's been there for 10-15 years, and to simulate that as close as we can, that's stress history. We basically model the construction of these two tunnels and to set up the stress history by running the problem in the consolidation time. Then we proceed with setting up this model and construct downward. So a lot of these things is it's the level detail sort of moves forward in a project. A lot of things that you may not anticipate in the beginning, but having a model that allows you to incorporate some of these questions is very important, and that is why it goes back to this whole connected digital environment, whereby the model can be easily updated to suit any problems that might arise, you see. So models on the left, just to give you some additional ideas of what you can build with it. I want you to think about part of looking at these models in terms of geometry, but also think about in terms of what could be the soil type and how would you set up the initial stresses, whether this is a short-term, long-term, or transient full couple flow analysis. This is something you must always think about, because it has to incorporate the simulation of the phases here. Okay, going to modeling and tunnels. I think many of you sitting in today have seen, probably heard and seen, even been through TBM machines. You look at it. I'm just giving you an example of a tunneling machine, a mechanical tunneling machine here. You have a slurry shield or earth pressure balancing TBM. You have the cutter head. You have the excavation chamber. You have the shield. Right, diameter at the front is normally bigger than the tail, so you have some sort of conicity to it. Then you have tunnel lining, and of course the conveyor system. It's here just for detail, but this also controls in terms of the earth pressure, so how much sort of pressure we can maintain here, this chamber here. Now the question is, like, how do you model this in any finite element analysis? What I discovered is that almost close to 9 years of work is one of the challenges is that everybody is using different ways of modeling, whether it is stress control, entirely stress-based type of analysis, whether it is a strain based, or whether it's a mix of it. In PLAXIS, you look at the using the what you call it, the control of the loss of the volume by putting a percentage of the change of the circle. This is actually strain control. There are a couple of methods in PLAXIS, but to some you may not find it so obvious, is that you have also a pressure type, or you can have a mixture of it. What is important, I've discovered in the last 10 years, is that before you do any analysis, depending on the contract, or depending what you want to find out, there are ways of modeling it. Now, one is that if a contract says that you need to take an account of certain percentage of volume loss, 0.5, 0.3, 0.1, or 1. So those have become your parametrics. That can be done using this contraction method as a quick way to gauge what sort of settlement that you're going to incur at the surface. Of course, this sort of modeling has to incorporate a proper advanced soil model, because you may put in this feature, but you use a linear elastic, you use a more Coulomb, you're going to end up with totally nonsensical results, right? So in terms of modeling, our approach is this, suggestion is this, that these are the causes of ground settlement, isn't it? Right? It can be right at the front before it. You have the stress relief at tunnel phase. You have the shield overcutting, steering effects, conical shape, tail void. Now, some of these things you need to figure out whether it is important or not to incorporate it. Well, if you want to start on modeling, perhaps you can start off with something just to get an idea what's going on. Then the contraction method by percentage may be a good thing to go. Then going down, you can see that what we have sort of proposing here is that you need to clarify and tell people that when you begin in modeling, what is your numerical tunneling machine? You've seen a physical machine, but this numerical machine that you're going to model, in terms of how you capture it, you need to sort of get it correctly. All right. This is what we call TBNN. And moving forward, this is the type of modeling that you can do using a Python script. And this is the whole optimization tool that, yes. Yes, Dr. Shukla.
Yeah, can you just speed up? I think we are just
Yes,
a
sure.
bit late. So if you can, I'm not saying that you will close it, but you can speed it up. Yeah.
Sure, yeah, sure. So now this is the tunnel application tool. This is something we have built to simulate the tunneling process. This was presented in one of the webinars, so you can take up this webinar and you can look at how this whole process will actually captured here. All right. So look for the tunnel application tool that allows you to capture build up this tunnel quickly here. Now the next one I've shown you earlier where we built up the structure, and beneath it is the continuing from that model. We built up this tunnel model, and then we look at the displacements. All right, and you can look at not just a one tunnel, a double tunnel, and you can see this tunnel itself. The modeling approach is that now the next one will be SCL. Just to give you an idea that what you can do is a very important process. It's even much more complex than your conventional TBM, because the sequence itself is the multiple sequences, and more so right now the modeling of the tunnel lining is now can be properly captured using a constitutive model called the a concrete model. This is a damage plasticity model whereby the hydration process, where the stiffness and the strength is properly captured with time. And it shows the differences between modeling with the concrete model and without the concrete model. Yeah. So typically this is the type of things that you can deal with in the tunneling. Now I'm going to begin and by sharing with you one case history or maybe two, because we are running short of time. And this will also involve a video. And I would advise you to look through this. I will encourage you to look through this presentation. It's actually available in one of the segments in the Year in Infrastructure. And this case is the West Island Line in Hong Kong, involving geotechnical analysis of underground infrastructures. And this is for contract 703. And if you've been to Hong Kong, and this is Hong Kong Island, and this is where that little part here on the west-hand side is where they needed to extend the existing island line a bit more towards the west side of the island. But to do so, there's quite a lot of work here because you need to build the shaft, and there was also an existing overrun tunnel which they need to replace with something bigger and build next to it a new one. So the overrun is just one tunnel. You could end up with two tunnel because east and westbound. So the next set of videos will show you that. And I want you to picture this when you look at the video, because this is the so-called Sayong Pong shaft. And this is the existing overrun. And this is the one of the new tracks that you need to build. So this is one of the shafts that you need to build in to connect the to construct. And to remove this old tunnel, you need to use another tunneling system. It's not a tunnel boring machine. It's a tunnel dismantling machine, which in one of the last video, you show you the ideas and how it was made to work. It was specially designed for these sections, you see. All right. So let me show you the shaft first. You can look at the shaft. Again, you need the PLAXIS 3D to construct analysis because you can't do it in plane strain. And this is the type of terrain they're dealing with. It's just not a singular layer or uniform layer. So apologies, I need to speed up the slide, but rest assured that you have the PDF slide that you can refer to it. So this is how it looks like. This is a station. This is Sayong Pung shaft. This is where they need to actually do the things that, and this is the overrun here. And of course, part of it is to look at the damage impact analysis here, because the tunnel, one of the tunnels is actually very close. It's just less than 1 to 2 meters of clearance from the toe of the foundation system. So with this slide, I would switch over to back to the team in India, because the video has been played over your end. So Pranav, go ahead.
In October 2007, the government approved the MTR's proposal to extend the island line to the west from Sheung. The first section of this work, and possibly the most challenging, is the construction of the dual-running tunnels through the densely populated Western District, from the existing Sheung station to the proposed station at Sai Ying Pun. The access shaft at King George V Memorial Park, where the ground is predominantly rock, excavation will be by a combination of drill and blast and mechanical or chemical rock splitting. From Sai Wu Lane to the existing Sheung station, where the ground condition is predominantly mixed ground, a slurry TBM machine will be used. From the base of the ventilation shaft on Devoe Road West, the existing overrun tunnel will be demolished using a specially designed tunnel dismantling machine, or TDM. The slurry TBM will be reassembled at the Sai Wu Lane shaft to construct the westbound tunnel. Through rigorous analysis of the geological conditions, the team confirms the use of a slurry TBM will better control ground settlement, and featuring a Moby Dick cut-ahead monitoring system will reduce the frequency of hyperbaric interventions. The machine's double man-lock provides safe working conditions and minimizes the adverse effects of compressed air working. The instrumentation and monitoring of existing buildings along the tunnel alignment is of paramount importance in alerting any undue movements or settlements. State-of-the-art real-time monitoring systems will be provided by in-house instrumentation specialists. There are other obstructions that the team are aware of, such as existing foundations and ventilation shafts, which will be removed or mitigated as required during the construction sequence from the TBM phase. The TDM will be delivered to the overrun tunnel down the existing vent shaft and assembled in situ. The TDM, with the ground supported by compressed air, mechanically removes the tunnel lining by first cutting the lower tunnel segment and removing it through the access hatch. This process is repeated until all segments interfering with the future tunnel alignment have been removed. Then the integral nozzles will shotcrete the excavation to ensure the work face is safe prior to backfilling. This cycle is repeated as it retreats along its path until the TDM reaches the existing vent shaft at Devoe Road West, where it will be dismantled and removed.
Okay, that was the 3 videos, and you're seeing on my screen right now that was the 3D model that we have used, kind of used to investigate the things that you have seen just now. And one of it was a tunnel also has to sort of cut through the existing tunnel system. Again, the things that I've been suggesting, that how you define and sort of put it prior to analysis, how you actually model the tunneling process is very important. So the TBM end type of destination, what you're doing around the tunnel needs to be properly explained to ensure that everyone in the team is clear how the tunneling process is being captured here. Well, this is actually the video, but no point showing it. Just to now, this is the how to dismantle. You've seen it. And finally, this is my last example for today. For this lecture, it's just going to take less than 3 minutes. It won the award for your infrastructure in the structural part. Although it's in the structural part, but actually it's looking at an excavation problem. I think this model is a very beautiful model because it showcased the good use of digital twinning and to look at the problem. So what is this? This is part of the deep excavation beneath the Admiralty Arch, and it develops actually optimizes. Now this is the Admiralty Arch itself. So you look at this whole video to give the audience, the stakeholders, and everybody involved in the project a firm idea what you're dealing with, right? So this is something you need to do. You have the refurbishment of the heritage building, something you probably you can see that even Mumbai itself, you have this Victorian type of buildings. And the new mall beneath it, somewhere on the other side, also the new basements that need to be constructed. And using the sort of digital twinning and visualizing technology, it allows to visualize the problem. Now you have the two system here marked by red and blue. Basically, these are the two existing structure around that you need to be very careful, because you need to build these new basements by extending it downward. And if you look at the next slide, let's see what's going on. Typically, is that you have the weight of entire structure at the top. At this point in time, this was not modeled, but just the load itself. You have that retaining system that you need to be construct. And what is the main drawback is that when you excavate, it's going to be causing amount of significant heave. And in this whole modeling, analysis, and design process, the ability to see the problem and visualize it, it's amazing, because this is the exclusion zone, right? And you have all the loads and forces coming down. And then due to heave, you might even encounter a tension in the existing foundation system. So what are the challenges? You have building movement, you have tunnel movement, just so to speak, to put it in a very simplistic way. And the solution is you did the first 2D, the client did the first use a 2D analysis to make a rough assessment. Then finally, as they progressed towards the contract, a full proper 3D was needed to sort of really look in the details. And you look at, that was a tunnel they were looking at, and these were the utilities that a smaller diameter tunnel that has to be checked, and this was modeled using just a beam to look at the displacements and the loads. And this is how the 3D model looks like. And then subsequently, once this was constructed, you just look at the sequence itself, right? Look at all the components, and having the ability to look at this model. In fact, in this day and age, with all these 3D virtual rooms, you can even spin and dive into this sort of environment here. And so right after it was done with the analysis, of course, information has been offloaded to the structural group to look at the impact in the structural sort of a check here. And well, this is a very nice, to me, it was a very nice way of demonstrating the ability, how we can make use of technology. As I said earlier in the beginning part of my lecture, is that we talk about going from ground to cloud, isn't it? So with this, I hope that I've given you some insights on the technology that we have been building for the last 2 years, and some has been in the group for some time. And it's just that we're going to make this a bit more better for everybody. So with this, I'd like to thank the team, DFI, and also my colleagues that's been supporting our work. Thank you so much. And right now, I leave this presentation back to the team, and we're gonna open it up for question and answers here. Thank you, everybody.
Thank you, William. Thanks for your excellent presentation.
Yes, thank you. That's sort of like a bit long, but I try to put in as much as I can, because it's a rare opportunity for us to showcase of ideas and a modeling approach here.
Yeah, I think, and I would request DFI India at least to have a let's say 2 sessions, maybe some another session in let's say in upcoming time, to accomplish or to detail it out some of the things which you have let's say referred very quickly. Anyway, we, on the behalf of DFI India, I thank for sparing this time and interacting with us and giving an excellent presentation. I just would like to, I have some questions from some participants, and I would just read out the questions. First question is from Stephanie. I just would like read it. I believe the disciplines involved in our work, both in design stage and in the construction stage, must include the mechanical engineers. This can give the team an added insight into what could be the possible or even dead, and responsibly participate in the design and manufacture of the specific equipment required to attain the best desired result. So what I understand is that let's say the Stephanie wants to mention that the mechanical modeling or mechanical team also need to be involved when we try to capture everybody into the globe, and when we take it from, let's say, ground to cloud, mechanical engineers are also required to be included. That's what I understand. I would request your comment.
Correct. That is correct, because there's no one unified single process that includes all components. Let me give you an example. If I'm dealing with a project whereby I'm building a building as a basement, and all the more the M&E, what we call the MEP, the mechanical, electrical, and it has to be involved. In fact, if you go to one of our old webinars, I think it was made last year, in our team, it involves 4 groups. It's from the building group, civil group, structural, and geotech group. Because the building group, in part of the solution, that it allows us to look at all this M&E stuff to incorporate it. So I suggest that you look at that. Webinar is a great webinar, and our geotechnical part was only 1/4 of the solution. Now, having said this, if you look at say infrastructure work, then I think at the beginning part, the M&E side will be very small as compared to other areas of geospatial, geological, and then even geotech. So it depends on what part of the infrastructure we're building. Now, the third case example is that you look at now renewable energies, looking at solar plants, looking at inshore wind farms. Then M&E will be definitely important, because how you arrange the structure of, let's say, the wind farms will affect how you line up the utilities and the placement, the hub stations. So I agree with you. And to do all these things, you need that ability to interoperate. Once we have that one common way of sharing information, which can be passed on from one team from the central hub, then it is easy. Not just passing, but the ability to update it and being informed that it's being updated, so that you're not using the wrong data as you move along. I'm sure many of us sitting in is that you have built a 3D model 2 days, and all of a sudden, you only found out that actually I've changed the design last week. So that interoperability I've shown you is happening, and what I've shown you in the first process is still work in progress. Is looking at structural and geotech. My own next project is actually looking at climate change, just basically looking at how the dikes has to be enhanced due to the rise of water level. Now, that sort of information would then be another part of interoperability that requires not M&E, but hydrologists, hydraulics, and all these things here. So yes, you're right, Stephanie. This has to be incorporated, and I share. I can feel your sentiments when it comes to this sort of things here.
Yeah, thanks. I just would like to read another question. The question is from Mr. Santa Raman Ramakrishnan. His question is, for a circular shaft modeling in 2D PLAXIS versus 3D, what will be the force difference or change in the design? Since it is governed by hoop stress, results from 2D will not be sufficient. He is asking your views on this.
Okay, now modeling a shaft in plane strain will always be something that perhaps at the earlier part of your contract you don't have sufficient time. You just want to make some checks, right? But it's not something that one should do. You don't have experience in terms of shaft design, because you have gone through the process of designing a shaft. You know how stretch the 2D analysis. But if you're moving the new conditions whereby you don't know what's going on, you're trying to look at how the construction process is causing response to the ground, I think the 3D analysis is very important. And the ability to model the joint sets, I mean, not the joint sets of the soil, but the joints of, let's say, a diaphragm wall. You can also see quite a lot of different shaft construction methods. And now, when someone asks me about 2D and 3D, it's a good thing. I will go for 3D, in my own opinion. But I must also think about how the groundwater is, because many a times people neglect how the groundwater responds. We cannot control that much of the soil stresses change because it's all being controlled by the water. If you know how the water is changing in the ground, to a certain extent, we'll know how the ground will react, right? So I have not seen any, I mean, I can't give you a overall conclusion that it has to be always done in 3D. I think it will need 3D. If I look at your drawings, if I look at the problem itself, the timing and what is around that shaft, I think 3D will be the way to go, because sometimes this shaft are not even entirely a circular shape. It could be sort of like an oval shape. And it can even consist of multiple circles joining and has a corner. So try to contact one of our engineers in India. He's sitting in today. His name is Rajendra Bish. If you are using PLAXIS, you can always give us an email or call, say, hey guys, I mean, I've done this, and then what do you think? We won't be doing the model for you for sure, because that is then we're doing consulting, but we can actually suggest, look guys, I think this is can be properly do this way, in my opinion. So we can actually share a lot of information with you with that here to sort of help you to expedite the work here. Okay.
So, thanks, William. Another question, it is from one of the student, I think, Miraj Thakkar. He is asking that he has tried some Bentley e-learning webinars and tried to understood PLAXIS. But do you recommend any, let's say, FEM in geotechnical or any book or a resource to read and to enhance the knowledge of students who can just started some modeling into PLAXIS?
Yes, I'm happy that this student is asked this, because when I look at it, I look back my close to 20 years here. It's always a continual learning process. I think that to move into computational geotechnics is that you need to really understand soil mechanics, because without the fundamentals, you will never be able to explain to yourself what's happening. Now, once you have that, you're having the fundamentals, having the basic knowledge of soil mechanics, then you can then look into technical engineering, because you really need to understand how some of these things are constructed. And for example, you look at excavation, you look at embankments, ground improvement, you need to continue to read and read and read. There are many books around, and of course, your professors, your friends, the industry, coming to webinars, connect with the industrial thought leaders. This will continue to help you to learn. And this is especially what DFI is doing, because what we are doing now, like compared 10 years ago, I'm still learning. I mean, I still make mistakes, but it is falling back into the fundamentals to ask yourself this question: why is it so? Then so you can correct the most mistakes. That is the most important thing. That conscious knowledge that, you know what, am I getting it right? If it's not, why is it not? And that ability to explain to yourself that, you know what, it doesn't fit in any of this theorem, I need to go back to check why. And that is that thing that you need to build, because people can teach, but you don't use your own ideas to sort of think about it, then it's going to be difficult to look at all this very complex problem. So many things, many webinars. It's just that your world, the world is your oceans, and be passionate with what you do. You need to be very passionate with what you do, because if you're not, it's going to be very hard to sort of like meet the challenges and overcome all these questions here.
Yeah, I hope let's say you have answered the question. The another
I hope so.
question
Yeah.
which I also would like to let's say ask you, but it's an interesting question from Mr. Anil Kumar SV. He's asking
Mhm.
that most of the times it is very tough to get the parameters for advanced soil models like soft soil, creep model. In that case, do you recommend to derive soil parameters or derive from correlations, or what would be the recommended approach?
Okay, good questions. Getting soil parameters is always very difficult, even for me. All right, even for me, it's going to be very difficult for all of us. Nothing is ever simple in soil mechanics and geotech. But how you derive the soil parameters depends on the problem that you are looking at. My professors used to teach me, first and foremost, right, you must understand the soils that you're dealing with. It's just not numbers. It is something that you need to feel. You need to characterize it. You need to understand how you're disturbing the ground. For example, in an excavation, it's mainly an unloading problem. If you look at embankment, it's a one-dimensional compression problem. You look at the foundation, an entirely different thing. Excavation itself, if I have given the ability to put in some ideas, okay, I want this certain test. It's not very expensive, as simple as an odometer, but the odometer, rather than just loading it, I want I want unloading and reloading cycle, because I want to measure the unloading response of the soil and to test that sample at that sort of a strain range. And how do I unload it? It's based on an amount of soil that I'm unloading. And in a triaxial test, many a time that you just do a CSCU, to me, it's not so appropriate, because I would prefer even to do maybe a CIU test, and to ensure that it is tested on the same range. Now, this sort of thing matters, and this can only be known if you understand what's happening in that, and then it allows you to define the soil parameters. So defining the soil parameters, it's something that well, if you want to fight a court case, you're going to look for criminal lawyers, and you can look for an expert. Either you want to become an expert, or you need to look for someone to ask you to do that, right? Now, number two, once you have the soil parameters, then it comes to the art itself, because modeling is that you still need to calibrate the model to fit the certain things that you want to capture. So this you must slowly learn. I did not learn this in just an overnight. It took me 20 years. In the first 5 years, I have to unlearn my soil mechanics. I'm very blessed that I have good teachers in Singapore and India. It's just that if you come to one of the courses, for example, the HS, it will be something will be very relevant, because if I can offer anything at this point in time to help you to speed up that understanding, is that to pick up one of our modules where we talk about the hardening soil model, calibration, and optimization. And that part is, I think, is available in one of our session there. I think was done by Dennis or Misha from a team. And I would encourage you to look at that, because that is a very nice foundation for you to build upon here. It's not easy,
Okay,
yeah.
one last. Yeah. I also agree. And this, let's say, the derivation of model parameters is one of the key and crucial things, because if you are choosing the wrong parameters, you will get the let's say different results. So
yes,
I'll just take one last question over here.
yes, sure.
That is from Michael Paul, and he wants to ask strut stiffness for D wall, that means diaphragm wall. We assume in a PLAXIS analysis may change at actual condition. It may be higher or lower size. If you would like to, let's say you would like to ask the comments from your side, it's regarding the stiffness of diaphragm walls.
Yeah. Okay. I think what you're trying to look at is that as the displacements get larger, you may incur cracking in the diaphragm wall, so that in your analysis you may be doing, say, an intact EI or partially sort of diminished EI due to cracking based on the strains. One way I would look at this is that to see the effects is that to do a model where the wall is totally intact. The second one is to run it maybe at some degraded value to see how the bending moment and the forces of displacement sort of increase or decrease. Number two is that you're looking at diaphragm wall. It's also whether to model this as isotropic or anisotropic, because you shall see that in one of the lectures myself and Rajendra did for India is that based on the work continuing from Professor Helmut Schweiger, is that it makes a difference in terms of values. And whether you model as a plate or as a volume also makes an effect. Now, I think you need to check these things, because when you check these things and it tells you that the variation is not more than 20%, then you know that it's not significant. But sometimes it is, then you got to make a decision which model will suit you. I can't tell you this because until I run the analysis. And that's what makes finite elements so important and so powerful, because many of us sitting in will think that I run one model, that's it, this is going to be the whole picture. Bear in mind that the model is always a model, right? And you can run a lot of models to try to simulate as many outcomes as you can. But of course, when you're sitting in William, we don't have the time. I don't have the time myself, but that is our due diligence, and we need to put it back for the client to say, well, I'll check it for you. I run these 10 different types of conditions. I see that I can get a better picture of what's happening right now. That what makes us good as geotechnical engineers, the having ability to give the additional insight into the analysis. So coming back, it does make a difference, and you need to ask yourself how you should capture this here.
Yeah, I also let's say thanks to PLAXIS for including concrete model into the recent development,
Yes,
because
yes,
that was missing. And I would say this is one of the best development which I am seeing, that it would solve so many interface problems also, because
yes,
modeling always using the plate models or plate is not a correct and right approach. You know, you need to have some particular model which can rightly let's say represent the concrete elements and the plastic deformations and plastic cracking as well.
correct.
Yeah,
you reminded me to mention the concrete model, because it's not out of explanation. My mind was just skipping too fast, trying to give to elucidate some of these things. I don't think I've I mean, this short webinar, I mean, I try to congest and put in as much information as I can. But you have anything more questions, you can always ask. And I always welcome all these debates and sharing sessions. Yes, you're right. You talk about this concrete model, previously was known as the shotcrete model. It's a damage plasticity base. Now, bear in mind that this concrete model is to model unreinforced concrete. So you cannot model reinforced concrete. That is the next big challenge. It's like diaphragm wall, you have steel bars. So some pretty smart ones are able to sort of do some very interesting mathematics to sort of like, well, incorporate this. And that's why it makes some of these companies just so brilliant in their work, because they have the minds to do so. And yes, the concrete model is one of the most amazing things. Perhaps even for the next seminar, some 3 months down the road or later, we can also do another round of webinar where we actually use this model, although it's called a concrete model. Because it is damage plasticity based, we can look at all these cemented type of soils. And in fact, this model is so popular with the ground improvement companies right now to look at the DSM, DCMs, and very popular in this region at the moment, jet grouted layers here. You can see that if you don't use the concrete model to look at all these cemented material, you're going to capture the wrong mechanisms here. Yeah. Thank you so much. Yeah.
With this, I would say we just would like to thank you again on behalf of DFI India for this excellent presentation, and let's say sharing your views and observations and let's say suggestions with all our participants. I also would like to let's say inform our participants that DFI India is working hard for all these let's say groundbreaking webinars. And there are let's say another groundbreaking webinars are planned Another session is planned in the month of the May, which is let's say webinar number 5. The technical session is let's say ground improvement for railway embankments on soft marine clay and expansive soils. This would be a case study webinar, will be conducted, and the speaker is let's say N. Ramakrishna Raju, Vice President and Head Engineering Tata Projects. And the professional development session, finding a mentor. The speaker will be our Sri Lakshmi Natarajan, General Manager, Engineering and Business Development, Geekan American Corporations. So stay with us, and we again would like to thank. With this slide, I would hand over the sessions to our DFI India colleagues in India.
Thank you, everybody. Thank you so much. Good night here. Yeah.
Thank you. Thank you, everyone.